When we look for activities that engage our students, we are building on that 5E model. So that it's in the cards video that you saw was an example of an engage activity. It gets the kids active, it gets them thinking, gets them sorting and talking to each other. And then from that, you would want to build out into the explore, explain, elaborate, and evaluate. This is my favorite graphic of the 5E model because evaluation is not after elaboration. Evaluation is at every single step. The formative assessment has to happen really at each part of the 5E model. So as they engage and they're talking, you're evaluating so you can see what needs to happen next. As they're exploring, explaining, and elaborating, you're still there as that teacher, as that mentor, and as that coach, looking for those problem areas, looking for those areas where there are common misconceptions, and moving the students along towards mastery. So for this activity, it's all about designing a claim, evidence, reasoning of periodic trends. All periodic trends are based on Coulombs Law. Coulombs Law says that the force of attraction is related to the size of the charge, so Q1, Q2. For us right now, we're talking about the proton's charge being Q1 and the electron's charge being Q2, and also the distance. So the farther away those two things are, the less force of attraction there is. The closer together they are, the greater the force of attraction. There is a PhET activity called Coulombs Law that you can use as part of your Explore or as part of your Engage. I encourage you to look at this and play with it yourself, but basically it allows the students to move them farther and closer apart, and they see the force exerted. It also allows them to vary the charge of each particle and see what the overall effect is on the force of attraction, or they can also see a force of repulsion if they're the same charge. Once they have an understanding of Coulomb's Law, remember, this will carry them all through chemistry when we talk about states of matter or when we talk about intermolecular forces. Those are all based on the attraction and repulsion of one atom to another or one molecule to another. So students need to use claim evidence reasoning as a tool to argue and logic out why something is the way it is. For example, the claim is that nitrogen has a greater atomic radius than fluorine. The evidence, nitrogen is farther to the left. The reasoning, since atomic radius increases across the periodic table from right to left, which is true, nitrogen has a greater atomic radius. Everything the student said is fine. There's nothing that's not factual. However, correlation is not the same thing as causation. We want the student to understand why it is larger or smaller, not just because it's farther to the left. So how can we take an answer like this and make it better? We could also frame the claim in terms of atomic radius. We can look up actual data and feed that to the student. So we're giving them the claim and we're just asking them for the evidence and the reasoning. You can make it a very general claim, or you can construct a claim based on data. And part of the Explore in the 5E model could be that they actually have to go out and find atomic radius numbers for given elements and then use them later on. Nitrogen has 7 electrons and 7 protons. Fluorine has 9 and 9, both true facts. The fewer the electrons, the smaller the radius. This is very common for students to do. The one with fewer electrons means it's smaller. And yet, the claim is directly in dispute of that. Nitrogen has a larger radius and has fewer electrons. So down here, when they say the fewer the electrons, the smaller the radius, they're actually contradicting the claim. This idea of argumentation is a skill that has to be practiced. And this skill is where you really dive down into what the student thinks and why. So as my students generate these responses, I'm not saying, ooh, bad job, oh, this is horrible, oh, this is great. I'm saying, okay, that's pretty good data. Is there a way to do it a little bit better? If you look at your reasoning, do you see that you're making a mistake compared to your claim up here? So if there is a mistake, I'd like you to fix it. This is not a situation of right or wrong. This is formative assessment, productive struggle. So the student should look at it and go, oh, okay, it's good to make mistakes because when we make mistakes, we learn. Here's the claim with the numbers in it. The evidence should not be opinion of any kind. The opinion is actual factual data. So the electron configuration for nitrogen and the number of protons is not opinion, is not explanation. It's just data straight from the periodic table. Notice that they are explaining here, and as they explain here, they're then furthering on in that 5E model. The reasoning, both of them have two occupied energy levels. Since fluorine has more protons, the protons have a stronger pull. That is an excellent answer. Now, what if they had just said two energy levels? That, I would point out to the students, is, wow, don't they both have all the energy levels? We really need to say occupied energy levels because every atom has all the energy levels. They're just not all full. You can link that back to the activities such as Hog Hilton, where you said all the floors were in the hotel, and yet not every floor was full every time we put pigs in the hotel. So it's important to say the occupied energy levels. All right, let's look at another claim. Rubidium has a smaller first ionization energy. This would be something that is given to the students. You could also say, look up the data, explore the data, and find the first ionization energy for each element. Based on that, make a claim. Which one is greater or which one is smaller? The evidence, Rb has more energy levels than sodium. That's an opinion, and it's not exactly right, because remember, all atoms have all energy levels. And they're making a statement about more or less without really giving us data. They're not answering the question about what is the data or the evidence. Their reasoning, more energy levels means a smaller ionization energy. Their statement does not tie in to Coulombs Law and does not explain the connection. They're just making it sound like it's true. And just because they say it with conviction does not mean they're doing a very good job of explaining it. So let's see another possible answer. Rubidium is krypton 5s1 and 37 protons. They don't have to write out the entire electron configuration. They can do the noble gas configuration. Sodium is neon 3s1 and has 11 protons. They can list all the data they know. They don't have to use all of it, but they can list the data. What's important is what comes up with how they explain it. Krypton's valence electrons are farther away, the 5th energy level. Sodium, its valence electrons are in the 3rd energy level. This is basically restating what's shown in the evidence. Coulombs' law says the farther away from the nucleus, the less pull on electrons. We're not quite there yet because they have to connect less pull on electrons somehow with ionization energy. With less pull on electrons, it has a lower ionization energy. They're identifying that they understand what ionization energy is and how that relates to pulling on electrons. Also on Canvas is a link to this website. For now, I'm going to pick atomic structure, and I'm going to pick this thing right here called photoelectron spectra. And photoelectron spectroscopy, for those of you who have not heard that before, is basically we shine X-rays at elements and we knock off all the electrons. The x-axis is the amount of energy it takes to knock loose the electrons. The height of the peak tells you how many electrons are there. And this is how we measure and know that there's 2 electrons in the 1s and 2 electrons in the 2s and 2 electrons in the 2p. one of the activities on Canvas is called eject, or using PES data. And so this links in their knowledge of the atom and makes them look at real data to understand how the number of protons, their distance to the nucleus, affects the amount of energy it takes to knock them loose. They can see that the ones closest to the nucleus, the 1s, require the most energy, and then there's a big break, and then you have 2s and 2p. If you go to neon, again, you see 1s, 2s, and 2p. But notice, if we look at them side by side, there's carbon and there's neon. Notice that the carbon's 1s requires 28.6 megajoules per mole of energy, whereas the neon is 84. And again, we want them to explore and reach some conclusions so they can apply this when it comes to periodic trends. Yes, it has 2 electrons in it, but can they explain why this particular one has a stronger pull on electrons than the carbon? And neon has 10 protons, Z is 10, and carbon only has 6. So the number of protons definitely has an effect, according to Coulombs Law, on how much energy it takes to remove those electrons. Let this tool be one more way to get your students to explore the data, to find connections on their own, instead of you just telling them everything. Back to our claim evidence reasoning, this last one is a good answer. Let's look at another claim. Things don't always have to be in the same row or the same column. You can extend your students' knowledge by asking them more challenging questions. The Cl ion, notice I didn't say what the charge of the ion is, has a larger radius than the Ca ion. So at this point, hopefully they've been doing electron configurations, not just for atoms, but also for ions. So they should know that Cl has a charge of -1 and Ca has a charge of +2. So you can give them the claim, or you can ask them to make the claim, or you can have them look up the data for the claim. The evidence, chlorine has 3 energy levels and calcium has 4. This is, again, not a way to punish the kids and not a way to say, aha, you're right, you're wrong. You're looking for misconceptions in the student's thinking. Because if we catch them early enough, they don't become ingrained. They're not talking about the ions in this case. They're talking about the regular atoms. Let's look at another example of evidence and reasoning. Chlorine, the negative ion, has this electron configuration. Calcium ion has the same electron configuration, and they indicate the number of protons. Again, data comes straight from the periodic table, and there's really no thinking about it. It's just reporting the data. The reasoning, because they both look like argon, okay, that statement in and of itself could be done better. What do you mean they look like argon? But that's something students are going to say, and you might just point out, you could say they have the same electron configuration as argon. They have the same number of occupied energy levels. Good so far. Calcium ion has more protons, which is true. We see that in the evidence, pulling on the same number of electrons. So the cloud of electrons gets pulled in tighter in calcium, meaning a smaller radius. It rambles a little bit, but the student really understands that when you have the same number of layers of electrons, that's when you talk about the number of protons. If the discussion was about radius and you had totally different numbers of layers of electrons, you don't worry about the protons. You just say, this one has more occupied energy shells or has more occupied energy levels, thus it's bigger. So here's an example of a claim evidence reasoning that you can give your students that asks them to make the claim. So which element has a greater electronegativity, bromine or potassium? Now, some of my students will look up the data on the periodic table and they will say, this one's greater because this is its electronegativity value. But again, I don't want them to just give me facts. This is the way it is. I want them to explain why they know this to be true. that shows that they have a very deep understanding of how one thing can attract or repel another. I looked up the actual data, and that's the number of Paulings for bromine and also the one for potassium. When in doubt, look up the numbers yourself or give it to them in a data or ask them to find the numbers. You always want to make sure you know what you're talking about as a teacher. Bromine has a greater electronegativity. Let's look at all the different evidences somebody could come up with. These are all the evidences that somebody could come up with. Bromine is farther to the right. That's true. Bromine's a nonmetal. Also true. It only needs one more electron. You are right again. Potassium's a metal. Of course it is. Potassium is farther to the left. Yes, it is. Potassium loses one electron to look like a noble gas. You are batting 1,000, young man or young lady. You are not getting them wrong. However, this isn't data that we need because in the end, electronegativity is influenced by the protons pulling on the electrons and how far away those electrons are. For electronegativity, we're talking about bonding electrons, so we're talking about valence electrons. So the piece of evidence that we would want is that piece of evidence at the bottom. Let's look at some reasoning that they could use. Electronegativity is a pull on electrons. Bromine has more protons. Well, that is true, yeah, but that doesn't really connect one to the other. Bromine has more protons. Protons pull on electrons more. Sure, but then you're just saying as long as you have more protons, then you're going to have a greater electronegativity. They're not connecting that they also have to think about distance from the nucleus. Both of them have 4 occupied energy levels. Bromine has more protons and a greater pull. Notice they don't bring up Coulombs Law, but they kind of mention the idea of Coulombs Law because they're talking about greater positive charge. My student would still get credit for this, and it's a good explanation for electronegativity for the comparison of bromine to potassium. For this one, I'm going to give you claim evidence reasoning for the same idea, but argued several different ways. So this is the first one. The second one in green, the same claim, a different set of evidence, and a different reasoning. Purple one, same claim, a much shorter evidence, and a much shorter reasoning. You'll see a lot of students who argue like this, saying, you know what I meant. Here's another one. And you would see all of these probably in your class. So I like to have my students whiteboard this. And when they whiteboard it, I walk around the class and I will pick up 1 or 2, sometimes 3 or 4, but usually 1 or 2. And as I bring them up to class, I ask the students to look at it and say, what do you think? It becomes a I do, we do, you do, where I've showed them an example of this. And then we all do a simple one as practice, and then I let them start to work on some of these claims. It's at this point I ask the students, what do you think? What do you think could be better? Or is there a wrong statement in there? Then as the students start to self-correct, oh, I don't think that was right or whatever, you'll see that the other students in the room start to correct their answers. And at the end of the lesson, they all have a correct answer in front of them. And ultimately, that's what we're trying to do. We're practicing a skill that gets them to do the 5E model to really explore and evaluate themselves till they've mastered the concept. I went online and I found some graphs of periodic trends. Now remember, your students have generated periodic trend graphs if they've done the It's in the Cards activity. But you can take these and you can hand these to your students and you can just say, what does this tell you about ionic radius? And then why? And so the students have to realize that there's a big jump and then it goes down and then a big jump and then it goes down. I'm not worried about this stuff in the middle because that can make things kind of difficult sometimes. I'm worried about why does it jump up all of a sudden and then go down. So my students have to explain why the data does what it does. I have mine do this in a group where each person is a different periodic trend. So one is ionic radius, one is atomic radius, etc. And then I have them explain to the rest of the students in the group what's going on. So ionic radius versus atomic radius. So why is there that jump? Why is there this squishy part in the middle? Because fluorine is a negative charge and sodium's a positive charge. You don't get this continuous line like you do for the elements. But they have to be able to explain what's going on in the graph. I have two more. This is electronegativity on the left and first ionization energy. And again, they're having to explain why the graph looks the way it is. Now, if you want to push this a little bit more into the elaboration mode of the 5E model, maybe you have the students actually pull the numbers for these parts right here and explain why it goes up and then down. And that's where having electron repulsion within the orbitals comes into play. When you have two electrons in an orbital, those electrons push on each other. So that force of repulsion kind of counteracts the force of attraction between the protons and the electrons. If you wanted to have your students move on to that elaborate, they could totally argue out these small finer points in the graph where they go up and down and they don't quite do what you expect them to do. So hopefully you've seen some examples of some good claim evidence reasoning, and you've also seen some examples of some bad claim evidence reasoning. It's a skill, even for teachers, that you have to learn, and what we're looking for is true mastery of how the nucleus affects the electrons. There is no such thing as periodic trends so much as there's how does the nucleus affect the electrons, and how the nucleus affects the electrons is going to affect the way that element reacts.